76 days remain before everything might change. While most of the world celebrated the new year, raising glasses to close out what some called the year of the comet, 3I Atlas was already slicing through the void, racing toward Jupiter at nearly 40 kilometers per second with no sign of deceleration. March 16, 2026 has quietly become a countdown, embedded in calendars across observatories and space agencies. 3 details frame this story, and none of them fit the narrative we've been told about natural objects passing through our solar system. First, magnetic dust-like particles roughly 10 microns in diameter are falling through Earth's atmosphere. Not occasionally, persistently. These particles are too large, too uniform in size, and too consistent in their arrival pattern to be random debris from a fragmenting comet tail. Natural fragmentation creates chaos, a spectrum of sizes, irregular shapes, unpredictable distribution. What we're detecting instead resembles precision, as though each particle was manufactured to a specification. Second, the object glows blue, not the warm orange-red of a body heated by proximity to the sun, but a cold, eerie blue luminescence that intensifies even as Atlas moves away from our star. This contradicts what we previously thought about how objects behave in deep space. Cooling curves are predictable, governed by thermodynamics that don't bend for mystery. Yet here we are, watching something that defies the expected fade, as if it carries its own light source independent of the sun. Third, its trajectory already exceeds escape velocity from the solar system. It's moving fast enough to leave and never return, and yet it doesn't. Instead, it bends inward, altering its path with surgical precision toward Jupiter, as though the largest planet in our neighborhood isn't an obstacle to avoid, but a destination to reach. Rocks don't do this. What we're watching behaves like something with intent. Let's look closer at the data. The dust cloud Atlas left in its wake doesn't behave like the chaotic spray of a comet shedding mass. It behaves like a controlled release. When scientists measured the optical depth of this cloud, the value returned as exactly 1. Not 0.8, not 1.3, but 1, a precise mathematical threshold that represents perfect concealment without complete disappearance. Nature doesn't do exact. Nature does approximate, variation, noise. This is signal. Spectroscopic analysis adds another layer. The composition is almost pure nickel, with effectively no iron. Here is the crucial detail. Nature doesn't produce metallic nickel in isolation. Nickel-iron alloys, yes, meteorites carry both, fused together in predictable ratios. But pure nickel, refined nickel, is a signature of processing, of extraction, of technology. It's what you'd expect from a manufactured component, not a rock that wandered in from interstellar space. Then there's the rotation. Atlas spins with a period of exactly 7.74 hours. No wobble, no drift, no precession. This is the rotation profile of a stabilized object, a gyroscope, something designed to maintain orientation. Tumbling asteroids exhibit chaotic rotation, their spin axes shifting as they respond to impacts and tidal forces. Atlas rotates like a satellite in controlled flight, maintaining attitude control for instruments that need to point in specific directions. So, what does this actually mean? If we strip away the caution and diplomatic language, we're left staring at an object that behaves less like a visitor from the Oort cloud and more like a machine. a machine heading toward Jupiter, not by accident, but by design. And Jupiter isn't just any planet. It's a dynamo, a generator of magnetic fields so intense they can fry unshielded electronics within minutes. It's a planetary-scale amplifier capable of modulating signals and broadcasting them across distances that would otherwise swallow any transmission in noise. March 16th marks Peryov, the closest approach to Jupiter, the moment when Atlas will thread through the giant planet's magnetosphere at optimal range for energy transfer or signal relay. Miss this window and the alignment dies. Wait another orbit, and you're talking decades or centuries. This is a one-time event, and the clock is ticking. But the story doesn't stay out there in the dark. It's already touching Earth. Silver noctilucent clouds have been reported drifting far beyond their usual polar boundaries. Satellite constellations have logged intermittent interference. Radio telescopes pick up flickers of static at frequencies that don't align with terrestrial broadcasts. And buried in data logs are silent failures, small anomalies shrugged off as equipment aging, but all clustering in the same narrow time frame. Then there's the James Webb Space Telescope, floating at Lagrange point L2. Webb was designed to operate for a decade without significant maintenance. Yet suddenly, maintenance has been scheduled for early 2026. Launch manifests quietly list new payloads bound for L2, instruments whose specifications aren't publicly detailed. It's as though someone already knows something is out there, something worth watching with equipment that wasn't originally part of the plan. This isn't the first time. Oumuamua passed through in 2017, accelerating slightly as it left. Borisov followed in 2019, anomalous in subtle ways that didn't quite fit the standard comet profile. But now the intervals are shrinking. The visits are closer together. A rhythm is emerging, like a pattern of check-ins, like someone running a survey, collecting data, not to make contact, but to record, to catalog, to observe. Maybe we were never the explorers. Maybe we were always the observed. And maybe 3i Atlas, silent and deliberate, and accelerating toward the largest target in the solar system, isn't here to speak to us. Maybe it's here to report. 76 days remain. Whatever happens at Jupiter will decide whether we misunderstood everything. If this story has you hooked, consider subscribing. We're going to follow this all the way to March 16th, and you won't want to miss what comes next. As we established in the opening, the dust falling through Earth's atmosphere isn't behaving like debris. It's behaving like a payload. To understand why this matters, we need to zoom in on what these particles actually are, and why their uniformity is so deeply troubling. Let's look closer at the data. When atmospheric sampling stations began detecting these 10-micron particles, the first assumption was contamination, something terrestrial. But the magnetic signature didn't match. These particles align with magnetic fields in ways that suggest embedded structure, internal organization at the microscale. They're not just metallic dust. They're engineered grains that survive re-entry heating and atmospheric turbulence without disintegrating. 10 microns is not arbitrary. It's the threshold size where atmospheric drag becomes significant but not catastrophic, where a particle can slow down enough to settle gently rather than burn up. Smaller particles get swept away by upper atmospheric winds. Larger particles hit harder, embedding in soil where recovery becomes difficult. But 10 microns lands softly, stays intact, and waits. If you were designing a particle meant to survive planetary entry and remain functional, 10 microns is exactly where you'd engineer the diameter. The composition adds weight to this hypothesis. Pure nickel with no iron contamination. Spectroscopy doesn't lie. Nickel-iron alloys are everywhere in the solar system, the legacy of planetary differentiation billions of years ago. But isolated nickel requires separation, refinement, deliberate removal of iron. This contradicts what we previously thought about interstellar objects, which should carry messy chemical fingerprints, not purified compositions. Here is the crucial detail: the isotopic ratio. Nickel exists in several stable isotopes, and natural processes produce them in predictable proportions. The nickel in these particles doesn't quite match solar system values. It's shifted in a way that suggests either a different stellar origin or isotopic enrichment, a process that requires technology. Nature doesn't enrich isotopes. Reactors do. Civilizations do. Then there's the optical depth measurement of exactly one. Optical depth measures how much light a cloud blocks. 0 means complete transparency. Infinity means total opacity. 1 sits at a threshold where roughly 63% of light is absorbed, leaving just enough transparency to see through, but not clearly. It's the engineering sweet spot for a veil that conceals detail while confirming presence. Achieving optical depth of exactly 1 requires control over particle size, distribution density, and spatial arrangement. Random comet debris creates optical depth that varies wildly. What we're measuring stays stable, uniform, locked at 1. This is the signature of a controlled release mechanism, something that dispensed particles at calculated intervals. It's what you'd expect from a deployment system, not a fragmentation event. So, what does this actually mean for the behavior of the cloud? Building on this, we can model how these particles spread. Comet tails follow predictable paths shaped by solar wind, streaming away from the sun. The Atlas particle cloud doesn't follow this pattern. It expands spherically, symmetrically, as though released with equal velocity in all directions. This requires energy, a mechanism to impart momentum uniformly, something internal rather than external pressure from sunlight. The timeline matters. The particles began appearing in Earth's upper atmosphere roughly 6 weeks after Atlas passed perihelion, the point where solar heating peaks. But Atlas showed no visible coma, no tail, no signs of volatiles boiling off. The particle release came later, delayed, timed, as though triggered by internal logic rather than external heating. If Atlas carries its own power source, it can operate on its own schedule, independent of environmental triggers. The uniformity is the smoking gun. In every sample analyzed, from Alaska to Antarctica, the particle size distribution peaks sharply at 10 microns with minimal variation. Natural processes produce power law distributions, a broad spectrum where small particles vastly outnumber large ones. What we're seeing is a narrow bell curve centered on a target value. This is manufacturing quality control, batch consistency, the hallmark of industrial production. Given what we now understand, The question shifts from what they are to why they were deployed. If Atlas is a probe from beyond our solar system, then the dust isn't waste. It's function. Maybe each grain is a microsensor designed to sample Earth's atmosphere, measure chemical composition, detect biosignatures, and transmit findings back to the parent craft. Maybe the particles interact with our technology, testing our resilience and ability to recognize intrusion. Or maybe they're simpler, merely breadcrumbs left by something that knows it will pass this way only once. A deliberate trace, evidence of visitation, inert but unmistakable, so that when we eventually develop the tools to analyze them fully, we'll find the signature that says, "We were here, we saw you, we moved on." The dust falling through our skies connects directly to what's about to happen at Jupiter. If these particles are part of a coordinated mission, then their deployment timing relative to the Jupiter encounter isn't coincidence. It's sequence. Step 1. Seed the third planet. Step 2. Rendezvous with the giant. Step 3. Transmit, amplify, or whatever comes next when Atlas threads through that magnetosphere on March 16th. What makes you think about all this? Drop your take in the comments, especially if you've got a background in material science or atmospheric physics. We need more eyes on this. Building on the dust evidence, which tells us about intent and engineering, we now need to confront the movement itself, how Atlas moves, why it accelerates, and what its rotation reveals about internal structure. Because if the particles are the message, the trajectory is the delivery system. Let's start with the acceleration problem. When a comet approaches the Sun, it heats up, volatiles trapped in ice sublimate, jetting away from the surface. This outgassing creates thrust, a weak but measurable force that can alter trajectory slightly. This is the standard model. It works for Halley, for Hale-Bopp, for virtually every comet we've tracked. But it doesn't work for Atlas. Atlas is accelerating in a way that increased as it moved past perihelion and continued outbound toward Jupiter. Normally, as a comet retreats from the Sun, heating decreases, outgassing drops off, and any non-gravitational acceleration fades. Atlas does the opposite. Its acceleration increased with distance, peaked where solar heating should be minimal, and shows no correlation with sunlight intensity. This contradicts what we previously thought about how objects behave in the outer solar system. One hypothesis is the rocket effect from supervolatiles, exotic ices that vaporize at temperatures far below water ice, frozen nitrogen, frozen carbon monoxide, but spectroscopy hasn't detected these compounds. No nitrogen emission lines, no carbon monoxide signatures. The spectrum stays stubbornly metallic, dominated by that refined nickel profile, with no evidence of the volatiles necessary to explain sustained thrust. Here is the crucial detail, the acceleration vector. When outgassing drives a comet, the thrust direction depends on where the Sun is, which parts of the surface are heated, how the object rotates. Atlas's acceleration vector stays remarkably consistent, pointing almost exactly along its direction of travel, aligned with its velocity vector in a way that maximizes efficiency. This is what you'd expect from a rocket engine, directed propulsion that fires along the thrust axis. Nature doesn't optimize like this. Engineering does. The rotation adds another dimension. As we established, Atlas spins with a period of 7.74 hours perfectly stable, no variation detected across weeks of observation. To understand why this matters, consider what happens to irregularly shaped objects tumbling through space. Gravitational gradients, tidal forces, even gentle sunlight pressure all introduce torques that alter spin rates over time. Every asteroid we've studied shows some evolution in rotation, speeding up or slowing down or precessing like a wobbling top. Atlas shows none of this. Its rotation is locked, stable to within measurement precision, suggesting either an incredibly fortuitous shape and density distribution or an active stabilization system that corrects for deviations in real time. The first option requires coincidence stacked on coincidence. The second option requires technology, gyroscopes, or reaction wheels or thrusters that fire in precise bursts to maintain orientation. So, what does this actually mean for internal structure? If Atlas is stabilized, if it's maintaining attitude control, then it has a preferred orientation. Instruments need to point. Antennas need to align. The stabilization might serve communication, keeping transmitters aimed at specific targets, or propulsion, ensuring thrust remains aligned with trajectory. Let's look closer at the data on the blue glow. Thermodynamics tells us that an object's temperature depends on energy absorbed and radiated. For a passive body, this balance is straightforward. Closer to the sun means hotter, farther away means cooler. Atlas violates this pattern. Its blue luminescence intensified as it moved outbound, suggesting an internal heat source, something generating energy independent of solar input. Blue light is high energy, short wavelength, the kind of emission from hot plasma, electrical arcs, or advanced propulsion systems operating at temperatures far exceeding what solar heating can achieve. If Atlas is powered by something internal, a reactor or exotic propulsion mechanism, then the blue glow is waste heat converted to light in wavelengths that peak in the visible blue spectrum. Given what we now understand about propulsion and rotation, we can build a profile. It's not a tumbling rock. It's a controlled vehicle, maintaining orientation, firing thrusters to adjust velocity, following a trajectory that requires precision, aiming for a specific target at a specific time. The 7.74-hour rotation might not be spin at all. It might be a scan rate, the time for instruments to complete a full sweep, or the period of a communication beam rotating to maintain contact with multiple targets. The trajectory tells a story. Atlas entered on a hyperbolic path, already moving faster than solar escape velocity. But instead of passing straight through, it bent inward, executed a course correction that required energy expenditure, and aimed for Jupiter. This connects to Peri-Jove, the March 16 encounter. If Jupiter is the destination, then everything else serves that endpoint. Why Jupiter? The answer might lie in its magnetosphere, the vast magnetic bubble extending millions of kilometers into space. Jupiter's magnetic field is the strongest in the solar system, powered by metallic hydrogen churning in the planet's interior, generating particle radiation belts that would be lethal to unshielded humans. But for a probe designed to handle those conditions, Jupiter becomes a tool, a planetary-scale amplifier. Electromagnetic signals naturally attenuate over distance, spreading out and weakening until they're indistinguishable from noise. But if you can couple a transmitter to a massive magnetosphere, if you can modulate the output using planetary magnetic field lines as antenna elements, then you've built a broadcast station with power output that dwarfs anything achievable with onboard systems alone. Jupiter could serve as a relay, a booster, a way to send a signal across interstellar distances. This contradicts what we previously thought about interstellar communication, which assumes direct line-of-sight transmission. But if you're clever, if you've mapped natural amplifiers, gas giants with strong magnetic fields, then you don't need to carry all that infrastructure. You just rendezvous with the right planet at the right time and let physics do the work. 76 days from now, Atlas will thread through Jupiter's magnetosphere at perigee, optimal for energy coupling and signal modulation. The geometry is surgical, the timing is precise, and the physics is sound. If this is a transmission event, we're not just observers anymore. We're witnesses to a conversation that spans light years. As we established with Atlas's trajectory and propulsion, this isn't an isolated event. To understand the full scope, we need to zoom out and look at the pattern, the sequence of interstellar visitors that have arrived in recent years, because the intervals are shrinking, and that's not how randomness works. Oumuamua arrived in October 2017, the first confirmed interstellar object detected passing through our solar system. Elongated, tumbling, moving fast, and then it accelerated slightly as it retreated, a tiny boost that couldn't be explained by outgassing because no one detected any gas. Astronomers proposed light sails, but the math was tight. Still, it was possible. Oumuamua left, and most people moved on. Borisov showed up in August 2019, less than 2 years later. This one looked more conventional, displaying a visible coma and tail, outgassing detected. The composition was off, enriched in carbon monoxide relative to water, suggesting formation in a colder stellar environment. Borisov was weird, but explicably weird. It passed through and faded from attention. Now Atlas, arriving in late 2025, less than 6 years after Borisov, following a pattern where the intervals between visits are decreasing. Let's look closer at the data. If interstellar objects arrived at random, their timing should follow a Poisson distribution, clustering and spacing unpredictably. But 3 objects in 8 years, with intervals shrinking from roughly 2 years to 6 years, suggests something else. It suggests a schedule. Here is the crucial detail: trajectory clustering. When astronomers back-calculate the incoming vectors, the directions from which these objects approached, they don't scatter randomly across the sky. They cluster within a relatively narrow cone, a region that doesn't align with the galactic plane or any obvious nearby stellar nursery. This could be coincidence, a selection effect, or it could be real evidence that these objects originate from a common source, a network of launch points, or coordinated mission architecture. Building on this, consider what a reconnaissance mission looks like at interstellar scales. You can't send a single probe and capture everything. Space is vast, planets orbit, configurations change. So, you send multiple probes, staggered in time, each carrying updated instruments, responding to data collected by previous missions, refining the survey, checking whether conditions have changed. Oumuamua might have been the scout, the first pass, confirming basic parameters. Borisov could have been the follow-up, equipped with spectrometers tuned to sample atmospheric composition. And Atlas, arriving now with its particle deployment and Jupiter rendezvous, might be the reporter, the mission tasked with summarizing findings and transmitting a detailed update. So, what does this actually mean for the March 16 encounter? If Jupiter is being used as a signal amplifier, then the timing matters not just for optimal coupling with the magnetosphere, but also for alignment with the recipient. Interstellar communication isn't instantaneous. Signals travel at light speed, taking years or decades to cross distances. If Atlas's mission is to transmit, then its target needs to be positioned correctly relative to Jupiter at the moment of broadcast. Given what we now understand about the pattern, we can ask, where is this coming from? The nearest star is Alpha Centauri, roughly 4 light-years away. If a signal were sent from there today, it would arrive in 2029. If Atlas transmits in March 2026, that report would reach Alpha Centauri in 2030, roughly 13 years after Oumuamua's flyby. That's a plausible timeline for iterative reconnaissance. But Alpha Centauri might not be the source. The trajectory clustering points slightly away from the nearest stars toward a region where no obvious candidates exist within 10 light-years. This could mean the network is more distant, or the probes are passing through waypoints, navigating a grid of relay stations scattered across the local interstellar medium. Let's consider the James Webb Space Telescope floating at L2. Webb was launched in December 2021, designed for a 10-year mission. So, why the sudden maintenance scheduled for early 2026, just weeks before the Atlas-Jupiter encounter? Why the new payloads heading to L2, instruments whose specifications aren't detailed in public manifests? This connects to the earlier observation about someone already knowing something is out there. If intelligence agencies detected early signs of the Atlas anomaly, then positioning additional surveillance assets at L2 makes sense. L2 offers a million-mile buffer from Earth and provides continuous line of sight to both Atlas and Jupiter during the critical encounter window. The pattern extends to Earth-based observations. Radio telescope networks have quietly shifted schedules, reallocating time to focused campaigns tracking anomalous signals in the outer solar system. SETI programs, usually scanning distant stars, have turned inward, pointing at Jupiter, waiting. This isn't public, but the data is there in scheduling logs. Silver noctilucent clouds, normally confined to polar regions, have been reported at mid-latitudes. These clouds form at the edge of space where ice crystals nucleate on tiny particles. The recent clouds show different nucleation patterns, seeded by particles matching the 10-micron profile. The clouds aren't just beautiful, they're evidence that Atlas's particle deployment has reached Earth. Satellite interference reports have increased. GPS glitches, brief signal losses, anomalies in communication satellites attributed to solar weather or equipment aging. But the timing correlates with Atlas's passage, and the nature of the interference suggests electromagnetic disruption. If the particles are active, the interference is a side effect. This contradicts what we previously thought about how interstellar probes would behave. We imagined beacons, deliberate signals, attempts at communication. Instead, we're seeing something quieter, more subtle, a reconnaissance mission that observes without announcing itself. Maybe we were never the audience. Maybe we were always the subject, the data being collected. And maybe the network is a survey in progress, tracking how a species like ours evolves. 76 days remain. The Jupiter encounter will answer some questions and raise others. But one thing is clear: we're not alone in noticing what's happening. Someone, somewhere, is watching the data too. If you've made it this far, hit that like button. Content like this needs your support to reach the people who care about these questions. Given what we now understand about the pattern, the physics, and the particle deployment, we arrive at the question that matters most. What happens next? March 16th, 2026 isn't just a date on an astronomical calendar anymore. It's a threshold, a moment when something we've been watching becomes immediate, consequential. 76 days remain, and the signs are already visible. The noctilucent clouds are the most obvious. As we established, these high-altitude ice formations are nucleating on Atlas's 10-micron particles, creating visible displays far beyond their normal range. Observers in Central Europe, the American Midwest, even Northern Africa have reported sightings. Spectroscopic analysis confirms the altitude 80 kilometers up, and particle sampling confirms nickel-rich grains embedded in ice crystals. What makes these clouds significant isn't just their anomalous distribution, it's what they represent: proof that Atlas's particle deployment is functioning as designed. If these particles are sensors, then the clouds mark where they're concentrating. If they're communication nodes, then the clouds might be interference patterns, visible evidence of electromagnetic fields interacting with atmospheric moisture. Building on this, let's look closer at the data on satellite interference. GPS constellations have logged intermittent anomalies where receivers temporarily lose lock, dropping navigation accuracy from meters to kilometers. These glitches don't correlate with known disruption sources: no solar flares, no geomagnetic storms. But they do correlate geographically with regions where noctilucent cloud sightings are most frequent. Communication satellites have experienced similar issues. Transponders briefly go offline, data packets drop, error correction protocols compensate for signal degradation. The timing is suspicious, clustering in the weeks since Atlas passed perihelion, increasing as the particles settle through the atmosphere. If the interference is deliberate, we're being probed by actions that disrupt our technology in subtle, deniable ways. Radio telescopes have picked up transient signals, brief bursts of noise in frequency bands not allocated to terrestrial broadcasts or natural sources. These signals don't repeat, don't follow predictable patterns, and fade before triangulation can pinpoint their origin. Some think we're detecting Atlas itself, short-range transmissions as the object communicates with its particle network. Here is the crucial detail: the timing relative to March 16th. If Atlas is following a mission timeline, if particle deployment was step 1 and Jupiter rendezvous is step 2, then the interference, the clouds, the signals are all part of step 1.5, a testing phase where the probe verifies its network is operational. If Atlas is going to broadcast using Jupiter's magnetosphere, it needs confirmation that receivers are in position. So, what does this actually mean for the Jupiter encounter? Perigove occurs on March 16th at approximately 1433 UTC, when Atlas will pass within 600,000 kilometers of Jupiter's cloud tops, threading through the densest regions of the magnetosphere. Radiation levels there reach 10 million rads per year, enough to sterilize any biological organism and degrade most electronics within hours. A rock wouldn't care, but a machine would need shielding. The fact that Atlas is deliberately targeting this environment tells us about its construction. It's built to handle conditions that would destroy anything we've sent to Jupiter. Our probes approach from angles that minimize radiation exposure. Atlas doesn't seem concerned, suggesting either shielding technology far more advanced than ours, or a mission profile where survival beyond the encounter isn't necessary. The most likely scenario is that Atlas reaches Perigove, couples electromagnetically with Jupiter's magnetosphere, and initiates a high-powered transmission. The energy could come from onboard reserves or be extracted directly from the magnetosphere itself, tapping into the planetary dynamo, converting orbital energy into electrical power. The transmission might be brief, a compressed data burst encoding everything the probe has observed: Earth's atmospheric composition, spectral signatures of industrial pollution, electromagnetic profiles of our technology, satellite trajectories. Or it might be longer, a sustained broadcast that modulates the entire magnetosphere, turning Jupiter into a beacon visible across light years. This contradicts what we previously thought about interstellar communication, which assumes low power, continuous transmission over decades. But if you have access to a planetary amplifier, you don't need to transmit for long. You just need to transmit loud enough that the signal overwhelms background noise instantly and arrives at your destination with enough strength to decode. The alignment matters. March 16th is the optimal moment when Jupiter, Earth, and potentially target star systems align to maximize transmission efficiency. Miss this window, and you're waiting decades or centuries. Atlas has been accelerating toward this date with precision. The geometry is perfect, the physics is sound, and the countdown is running. What happens to Earth in the aftermath? If the particles are purely observational, we might see the interference fade, the clouds dissipate, and life return to normal. But if the particles are meant to remain active, or if they're designed to activate in response to the Jupiter transmission, then the anomalies might intensify. There's also the possibility that we're not the only recipients. If Atlas transmits using Jupiter as an amplifier, the signal propagates outward in all directions. Other probes in the network, stations scattered across the local interstellar medium, even civilizations we haven't contacted yet, might hear the broadcast and respond. We'd be bystanders, watching a conversation unfold in our backyard, unable to participate. Maybe we were never the explorers. Maybe that was always a comfortable fiction. But Oumuamua, Borisov, and now Atlas suggest a different story, one where we're the observed, the cataloged, the subject of long-term study by intelligences that operate on timescales exceeding our institutional memory. The network, if it exists, has been running for longer than we've had telescopes, possibly longer than we've had civilization. The visits might stretch back centuries or millennia, interpreted as omens or myths. Only now, with our satellites and spectrometers, are we beginning to see the pattern. 76 days remain. On March 16, 2026, at 14:33 UTC, Atlas will reach Perry-Hovey. Observatories worldwide will be watching, satellites will be recording, radio telescopes will be listening, and somewhere in the data streams, in the electromagnetic noise, in the modulation of Jupiter's magnetosphere, we might catch a glimpse of the message. We might not understand it. We might not even recognize it as artificial. But it will happen, and afterward, we'll know that we were seen, that we were measured, and that the universe is far less empty than we once believed. If you want to stay updated as we approach March 16th, make sure you're subscribed. We're going to be here reporting every development, every anomaly, every piece of evidence that brings us closer to understanding what Atlas really is. 76 days. The countdown has begun.